Alright, so in this video we are starting off on a new chapter. This is chapter 17. We're still talking about carbonyl compounds, but this deals with a different type of reactivity of carbonyl compounds that we haven't seen before. And specifically it's related to acidity of carbonyl compounds. Now if I was to draw out, for example, say a ketone like this, you might ask yourself, well, what are you talking about, acidity? Because doesn't acidity have to do with hydrogens coming off and forming H plus and things like that? Well, yes. So I don't have any hydrogens coming off the oxygen. How can this even possibly be an acid? Well, it turns out that it can, provided you have a strong enough base. If we take a look at let me add some more carbons here. Let's say we have this guy, 2-pentanone. Alright. I'm going to indicate this hydrogen here, this one here, and then these two as well. Alright. There's something special about these hydrogens. These hydrogens actually have, you know what, let me add some more carbons here just to finish this off. These hydrogens are special. These hydrogens on the carbon next to the carbonyl carbon. If you remember, we have seen before a way of recognizing what this carbon is. In fact, we gave it a symbol. We gave it a Greek symbol, and that symbol was alpha. Alpha just meaning the carbon next to the carbonyl. And if we employ the letters of the Greek alphabet, the carbon next to the alpha carbon is the beta carbon. The carbon next to the beta carbon is the gamma carbon. And then the carbon next to that would be the delta carbon. Now, we aren't going to go that far. We're really only concerned with beta and alpha, or more specifically with, in this case, for pretty much the whole of this chapter, we're not concerned with beta, gamma, or delta. We're concerned with the alpha carbon. Because there's something special about the alpha carbon, and thus the hydrogens on it. It's actually the alpha hydrogens that are acidic. Now you might be thinking, well, why? Why are those acidic? It's still a carbon-hydrogen bond, isn't it? Well, yes it is. And let's just compare it to, let's say we look at this. I'm just drawing two hydrogens here, but there are two more on each coming off each carbon here. This is ethane, and this is this ketone. Now the pKa of ethane here, in fact of all alkanes, is around 60, which means not acidic, essentially not acidic at all. Very, very high pKa, very unreactive, very boring, nothing you can do with that. The pKa of these alpha hydrogens, and thus of this ketone, is actually around 19. Now 19 and 60, this is a logarithmic scale here, so this means this ketone is not 41 times as acidic as this. It's more acidic by 41 orders of magnitude. Big difference. This is much more acidic than this. And you can imagine the reason for its acidity must be something to do with this carbonyl group. And indeed it is. If I had some sort of base here, let me draw out a much more simple ketone here. And this applies to aldehydes as well. So let's say we have, let's draw ourselves out an aldehyde, okay? I'm going to put my 3 hydrogens on here. We're only going to worry about one, but just drawing them all out. Here's a base. This has to be a particularly strong base, and we'll see some bollocks. We won't see some bollocks, but we'll see some, what I was supposed to say was we'll see some examples of strong bases as we get further into this chapter. But all I'm saying is here's some generic base. Well, like I said, we'll see what that is later on. The alpha hydrogen, or the alpha carbon here, which is this one, has on it alpha hydrogen. You can understand alpha hydrogens come off the alpha carbon. There's some reason why these hydrogens are very acidic, and for example this one is not. For the same reason, these hydrogens on the alpha carbons are acidic, these on the beta carbons, gamma carbons, delta carbons are really not acidic at all. So it's something to do with the alpha position. And what that something is a word that you've seen several times before. It begins with R, and it's resonance. It's all to do with the stability of what you get out. Here's our base, grabs that hydrogen, and I'm just going to put that negative charge onto that carbon. All right? And what we get out is something we haven't seen before. This is called an enolate. It's very reactive. It's not particularly stable. We have a negative charge on a carbon atom, so you can see, well, that doesn't sound like it's something, doesn't seem to make it very happy. Now this sort of negatively charged carbon, though, is actually more stable than you might think, again because of resonance. Simply because we can do this. We can funnel these electrons into that carbon-carbon bond, forming a double bond, and actually give us two different resonance structures here. Two resonance structures that in this case would look something like this. Alright, if I was to put my lone pairs on the oxygen here, there's two, and now we've got three on here. Hopefully these won't link up with each other as they usually bloody do. Alright, negative charge there. We have two resonance structures for this thing called an enolate. And enolates are going to be a big focus of this chapter, big focus. So if there's one thing you want to take from this chapter, it's about enolates and what they do. Enolates exist in two forms like this, one with a negative charge on carbon and one with a negative charge on oxygen. And if I was to ask you guys which one of these two is the one that's more reactive, out of these two sites, which is the more nucleophilic site, well, hopefully you would say here, because carbon is less electronegative than oxygen. It's less happy to bear the negative charge, therefore more reactive. So both of these exist. This is the one that is more reactive. However, we'll see them drawn both ways. Now I'm hoping you can see where we're going with this. The only way you can form an enolate is A, if you have a strong enough base, and B, if you have a ketone or an aldehyde or an ester or something like that that has alpha hydrogens. So what we're going to do in this video is spend a little bit of time seeing if we can recognize where in a molecule we have alpha hydrogens, and more importantly where we don't. So let's start off, actually we're just talking about something like this one. Let's start off with this ketone, and all you're doing is looking for the carbon next to the carbonyl. Doesn't matter whether it's symmetrical or not. If there are two carbons that are the same, well, that's fine. What I want you guys to be able to do is to put a circle or put an arrow towards or whatever, somehow recognize however many alpha carbons there are in a molecule. This starting ketone, I'm hoping you can recognize there are alpha carbons here, thus alpha hydrogens on either of those two carbons. Coming here, a lot of people make the mistake of thinking this is an alpha hydrogen, but it's not, because it's not coming off the alpha carbon. Remember, the alpha carbon is the one next to the carbonyl carbon and not the carbonyl carbon itself. Looking at this one, this is another mistake that people make. They will say, well, here are my two alpha carbons. That is true, but only one of these has alpha hydrogens on it. This one already has 4 bonds to that carbon, so there can't be any hydrogens there. This is the only alpha carbon that bears alpha hydrogens. Let's look at some more. Let's look at, now these are all relatively similar examples, but I'm hoping you guys can see something of a difference between, say, this and this. How many different types of alpha hydrogens do you see in this molecule? Well, the answer is 1. There are 2 types, but they're both the same, so 1 type of alpha hydrogen. How many types of alpha hydrogens do you see here? Well, if your definition of an alpha hydrogen is it's a hydrogen that's on a carbon next to a carbonyl, well, I'd say this is 1 type, and that is actually the same as this one. So I'd say that's my alpha type 1. But there is another alpha hydrogen, and that is on the different alpha carbon, and that's the one in between the two carbonyl groups there. In a molecule like this, we call this a beta dicarbonyl compound. Beta because they are 3 carbons apart, or 2 carbon up, well, 1, 3 with respect to each other. Would you guys be able to recognize which one of these has more acidic alpha hydrogens on it? The fact is, it's actually number 2, simply because for each of number 1, the hydrogen comes off, the electrons can go up here and go onto the oxygen. You can come up with 2 resonance structures, one with the oxygen with a negative charge on the oxygen, one with a negative charge on the carbon. Same thing here. When we have something like this, we can have a negative charge on the carbon, we can have a negative charge on the oxygen, or we can have a negative charge on the other oxygen. So 3 different places to put the charge, so therefore 3 resonance structures. We've seen before, the more resonance structures, the more stable the conjugate base. In this case, this means in the middle here is the more acidic hydrogen. So this hydrogen actually has a different and lower pKa than these 2 outer hydrogens. The situation is almost exactly the same for this guy. If you were to ask yourself, well, how many types of alpha hydrogens do I have here? It'd be very similar to up here. It'd be type 1, and then type 2. And once again, hopefully you can see type 2 would be more acidic. Now, both of these are diketones. This guy is called a beta keto ester, simply because here's the ester group. The alpha carbon of the ester, that's the beta carbon compared to the ester, hence the ketone is beta to it, hence the term beta keto ester, and we'll see more about these later on. But again, alpha hydrogen type 1, alpha hydrogen type 2. There are no alpha hydrogens over here because there are no carbonyl groups coming off anywhere over here. For the same reason, the hydrogen that's between 2 carbonyl groups gives rise to more resonance structures, hence it's more acidic. And when we look at this guy, this is essentially very similar. How many different types of alpha hydrogens can you recognize in this molecule? Well, there's definitely this one. There is definitely this one. One thing we're not going to get into at this point is which one of these is more reactive. The important thing is there are alpha hydrogens on each of these carbons, which for all intents and purposes can both act as acids. Alright. Now, what about this guy? You can see this isn't a ketone or an aldehyde or an ester. But if we go back to what we were saying before, the only reason these are acidic is because when this bond comes off, the electrons go onto this carbon. That can then kick electrons into here, break one of the pi bonds and put electrons up onto the oxygen. You need 1 pi bond to be able to do that, and the nitrile has 2. So it can act in exactly the same way. So how many alpha hydrogens do you see for this molecule? Well, it's just 1. So being able to recognize alpha hydrogens is really pretty important, because you can't do any chemistry, any of this alpha substitution chemistry, until you can recognize A, what an alpha carbon is, B, what an alpha hydrogen is, and where they are. Alright, so if you can do that, you are well on your way to figuring this stuff out. Okay? Good.